Hi all, this is Deepthi and I'm going to give a presentation regarding the IEEE paper titled A Slice-Based Estimation Approach for Maintenance Effort by the authors Hakem W. Almari, Michael L. Collard, and Jonathan I. Malatic. Coming to authors and journal, Hakem W. Almari is an assistant professor in the Department of Computer Science and Software Engineering. His research interests include software engineering, software evolution and maintenance, program slicing and program analysis. Coming to Michael L. Collard, his several research interests include software engineering, source code transformation and differencing, program comprehension, and software evolution. Coming to Jonathan I. Malatic, he is a professor of computer science at Kent State University. His research interests include software engineering, evolution and maintenance, source code analysis and exploration. This paper has total citations of 14. Coming to research questions, here the paper revolves around how can new approaches and tools must be developed to support maintenance working in the software domain, and an efficient slicing approach is needed to address many unpractical problems here. So to maintain large-scale systems, here we needed the new slicing approaches, and it also investigate how slices can change over the history of the software system. So coming to the motivation, here the main goal of this paper is to develop an approach to estimate the maintenance effort for open source systems using the new slice-based metrics. Here the program slicing is used as a basis for an approach to estimate maintenance effort. The main goal is the development of a very efficient and highly scalable program slicing approach here, and a tool to automatically produce slices for all variables in a large-scale system. Here the results depict that the approach accurately predicts effort in a high scalable manner. Coming to the introduction to software maintenance effort, usually software systems must always be maintained to remain useful, and estimating the amount of effort for maintenance tasks is a very important task for any system. So as software systems grow, maintenance typically becomes more complicated and costly. So the maintenance process should be well planned through an accurate effort estimation of the tasks. Usually this approach is not useful for large adaptive software systems. So in this case, the effort of a maintenance period depends solely on the number of source code changes made to the generated new software versions from an earlier operational versions. So here we introduce a maintenance effort estimation based directly only on the source code. So here we can identify and validate slice-based software measures that can represent maintenance efforts in an open source systems like GNU Linux kernel. Here the estimation approaches of maintenance effort are built and evaluated using residual analysis statistics. Coming to maintenance effort estimation process, here we have 5 phases in maintenance effort estimation process. They are in phase 1, we'll identify the measures which can indirectly represent the maintenance effort. With this, we can construct an indirect model for maintenance effort, and we'll use it to predict the indirect effort of open source systems. Coming to phase 2, here the extracted data includes the indirect maintenance effort identified and validated in the previous phase, and the data of other related measures as well to predict the indirect maintenance effort. Coming to phase 3, here we'll validate the correlation between the dependent variables and independent variables. And in phase 4, we'll apply multiple regression analysis which is used to build the effort prediction approach. In phase 5, we'll predict the indirect maintenance effort based on the models built in the previous phase. So in the indirect maintenance effort measures, we have two software measures here. They are lag time and source code. Lag time is nothing but it includes the duration from the date when a base version is released until the date the evolved version is released. So here we can assume that maintenance requests start when the base version is released and the tasks are completed when the evolved version is released. There might occur many problems regarding the lag time because it can be considered as an indirect maintenance effort indicator, including the high risk of over-reporting of the maintenance effort. Coming to source code change in the open source system can be used as an indirect measure for estimating maintenance effort. Source code change can be found using textual, syntactic, or semantic differencing. So here, many existing software metrics are based solely on the code syntactic information. Coming to program slicing and program analysis, here the program slicing is a well-known approach for understanding the change impact analysis on the software. Here we use forward stating program slicing, which it refers to the computation of program points that are affected by the other program points. Here we specifically taken here computes a forward static non-executable program slice for each variable in a system. Here the slicing approach addresses the traditional approach issues like by eliminating the time and effort needed to build the entire program dependency graph. So the slicing process here is performed using the source code markup language. Here the source code markup language is an XML format which is used to augment the source code with its syntactic information. Source code is first converted to source code markup language and then it can be the stream oriented approach to computing the slice is performed here. So coming to the slice profile and system dictionary construction, here we define our slicing criterion to consist of a file name, a function name and a variable name. The slicing criterion is the triple of f, m, b, where f is a file in the system, m is a function or method in the file f, and b is a variable in the given function m. This approach computes a slice profile that contains all the relevant statements from all possible slices over a given slicing variable here. This is the example sample source code, small sample source code, which is along with the final system dictionary. Here the dictionary includes two slice profiles, one for each of the sum of the variables and I. Here the @index represents the position of variables as declared in the function. In this way we can deal with the variables of the same name with the same scope. Here the slice profiles are computed by examining each line starting from the beginning and determining the forward slices. Here the final computation can be carried out for all the variables via a single pass through the dictionary. Coming to encoding slicing information, here the basic process of this algorithm starts with a single pass through the system dictionary, encoding each slice profile to a string value, which is then fed to a hash algorithm to produce the result. There are two steps in the SSE algorithm. First step is to encode the slice profiles and second step is to hash the string value. This step maps the encoding string from the step 1 to a hash value using the MD5 hash algorithm. To compute the behavioral change information across the entire history of a system, we'll check out the pair of consecutive versions of the system here from its previous repositories. Coming to slice-based metrics, here in the context of effort prediction, one can start the investigation of building an effort model by obtaining the empirical data and by estimating from such data a productivity function F. Here we consider two versions of Linux kernel, base version and the evolved version. And the table represents the slice-based extracted measures. So we considered base version and evolved version here. The measures of the maintenance data of base version are extracted as follows, like LOC size, file size, and slice coverage are determined from the source code of the base version. Hash size here is determined from the change information of the evolved version. And the lag time is determined according to the date differences between the base version and the evolved versions. So coming to the slice-based estimation on the Linux kernel, here we used Linux kernel as a way of demonstrating the use on the real systems. The Linux versions here are classified as stable or development versions. Here each major version includes several releases identified with either a 3 or 4 digit numbering schemes. So to examine this, Lehman's fourth law of software evolution. We'll study the maintenance effort what was spent on the system till now. So we start by considering the number of elements handled here. Here the first figure, figure 3, shows the number of files that were added, deleted and modified till now between the consecutive releases. Here from the figure we can interpret the rate to mean the fraction of source code that is modified in each release. So then the data supports the claim that work rate is almost constant here. And next we start analyzing the number of releases per month for the development versions as shown in the figure 4, second figure. In this the x-axis each step represents a year and each bar represents a month here. The vertical lines with the version label represent the start of the new major versions here. Coming to this in figure 5, we can see that the stable versions are released less frequently than the development versions here. So from this one can consider that the intervals between the major releases dependent independently from minor releases. So we can examine the intervals of time between these consecutive releases inside the major versions. Here the figure 6 displays the raw data of the intervals for each version. In the figure 6 we can see a significant gap between the versions 2.3 and 2.4 and between the versions here 2.5 and 2.6. So these two gaps are the results of the structural changes in the Linux kernel numbering scheme. In figure 7 we shows the statistics of the intervals for each version. So here we can notice that the bodies of the upwards of the stable versions are usually higher than those of the development versions. So coming to the evaluating the model performance, to study the quality of the proposed models for future predictions, we can apply the models to predict the indirect maintenance effort here. Model validation here is the most important step in the model building process. Here the results depict that the approach and estimation models accurately predict the maintenance effort in open source large systems in a very high scalable manner with a high rank of predictive power here. So coming to the conclusion, here we we perform slicing for multiple versions of the large systems using an Linux kernel as a dataset and use a case study to build and validate the model's performance using multiple linear regression models and all. Here the proposed maintenance effort estimation models can accurately determine the source code changes based only on the source code. Here the proposed models estimate the maintenance effort based on the number of changes made to maintain the system. So here the paper totally it addressed several practical concerns regarding the maintenance and evolution of open source large scale systems. Here the study is presented to understand and investigate how slices are changed during the evolution of the Linux kernel and all in the future versions. The data obtained by slicing the Linux kernel software system was used to identify and validate new slice-based software metrics for maintenance effort. This is the reference of the paper. Thank you.